Welcome to our channel. In this video, we will be discussing the amazing invention of the telescope. With the help of this powerful tool, we are able to gaze into the depths of space and uncover the mysteries of the universe. From amateur astronomers to professional scientists, the telescope has changed the way we understand and explore our place in the cosmos. So sit back, grab your eyepiece, and let's dive into the world of telescopes. Modern astronomy began with the invention of the telescope in the 17th century. The telescope opened up the solar system for viewing, revealing Saturn's rings and allowing the discovery of the outer planets. Observations made using telescopes were crucial in confirming that the Earth orbits the Sun. Eventually, the telescope gave access to the entire visible universe. Galileo was famously one of the first astronomers to look through a telescope, using its magnification in 1609 to discover 4 of Jupiter's moons, Venus's phases, and the craters on the Moon. However, he was just following a trend at the time. No individual is credited with the invention of the telescope. Dutchman Hans Lippershey was one of the first to attempt to patent a telescope design in 1608, but he was unsuccessful because the concept of the telescope was already widely known. The magnifying power of transparent materials with curved surfaces was well recognized, and lenses in the shape of a lentil had been used in magnifying glasses and spectacles at least since the 13th century. Records show that telescopes had been built and used to observe the Moon in the mid-16th century, but it was only with advances in glassmaking in the 17th century that high-quality instruments became widespread. These instruments, with their good lenses, produced clear images even of faint celestial bodies. Magnifying power. How does a telescope work? The simplest version uses 2 lenses placed at either end of a tube. The first lens concentrates the rays of light inward, so that the eye perceives them as coming from a larger source. The second lens acts as an eyepiece, making the light rays parallel again before they enter the eye, allowing them to be focused. The bending of rays by a lens is called refraction. Light travels more slowly in denser materials such as glass compared to air. This explains the mirage of a puddle on a hot road. The rays of light from the sky bend to skim the surface of the road because the light changes speed as it passes through the layer of hot air lying just above the sun-baked asphalt. Hot air is less dense than cooler air, so the light bends away from the vertical and we see the sky's reflection on the tarmac, appearing like a wet puddle. The angle by which a ray of light bends is related to the relative speeds at which it travels in the 2 materials. Technically, the ratio of the speeds gives the ratio of the sine of the incident angles, measured from the vertical. So for a ray of light leaving air and entering a dense substance such as glass, it is bent inward and its path becomes steeper. Refractive index. Light travels at an incredibly fast speed of 300 million meters per second in empty space. The ratio of its velocity in a denser material such as glass to its velocity in a vacuum is called the refractive index of the material. By definition, a vacuum has a refractive index of 1, while a material with a refractive index of 2 would slow light to half its speed in a vacuum. A high refractive index means that light bends significantly as it passes through the substance. Refractive index is a property of a material itself. Materials can be designed to have specific refractive indices, which may be useful in the design of telescopes or lenses for glasses to correct vision problems. The power of lenses and prisms depends on their refractive index. High-power lenses have high refractive indices. Refracting telescopes with 2 lenses have some drawbacks. One of these is that the final image appears upside down because the light rays cross over before they reach the eyepiece. For astronomy, this usually isn't a problem, as a star looks much the same upside down. However, it can be corrected by including a 3rd lens to invert the image again, but then the telescope can become long and cumbersome. Additionally, refracting telescopes often produce blurred color images. This is because different wavelengths of light are refracted by different amounts. Blue light waves are bent more than red light waves, and the colors separate out, causing the final image to lose clarity. While new types of lenses that are available today can minimize this issue, their size is limited. Reflecting telescope. To solve these problems, Newton invented the reflecting telescope, which used a curved mirror rather than a lens to bend light. By folding the telescope in half, it became easier to handle and avoided differential blurring because the mirrored surface reflects all colors of light in the same way. However, Mirror silvering techniques were not advanced in Newton's day, so it took centuries for the design to be perfected. Today, most professional astronomical telescopes use a giant mirror, rather than a lens, to collect celestial light and bounce it back to the eyepiece. The size of the mirror determines how much light can be collected, with larger mirrors allowing for the observation of very faint objects. The mirrors in modern optical telescopes can be the size of a room, such as those in the twin giant Keck telescopes on Mauna Kea, Hawaii, which are around 10 meters across. Even bigger mirrors, up to 100 meters in diameter, are planned for the coming decades. Very large mirrors are difficult to construct because they become so heavy that their shape distorts when the telescope tilts to scan the sky. To make them as light as possible, clever construction methods are needed, such as building the mirrors in many segments or carefully spinning them to be thin yet accurately sculpted. An alternative solution called adaptive optics involves constantly correcting the mirror's shape using a network of tiny pistons glued underneath to push up the surface when it sags. Twinkling stars. Beyond the telescopes themselves, the clarity of astronomical images is degraded by turbulence in the Earth's atmosphere. On even the clearest night, stars twinkle due to pockets of air moving in front of them, with those near the horizon twinkling more than those overhead. This blurring of stars by the atmosphere is known as seeing. The size of the optical components in the telescope also imposes an absolute limit on the concentration of starlight due to another behavior of light called diffraction, which is the bending of light rays around the edge of a lens, aperture, or mirror. To get the sharpest images of stars and planets, astronomers choose special locations for their telescopes on the surface of the Earth. These locations have thin air and smooth airflow, such as on high mountain sites or near the coast. Some of the best sites for telescopes include the Chilean Andes and the volcanic peaks of Hawaii. The ultimate site for telescopes is in space, where there is no atmosphere. The deepest images ever taken of the universe have been made by the orbiting Hubble Space Telescope. The James Webb Space Telescope is also designed to be more powerful than the Hubble Space Telescope. With a larger primary mirror and more sensitive scientific instruments, it will be able to observe objects that are much further away and much fainter than those that can be detected by the Hubble Space Telescope. Telescopes can operate at wavelengths other than the visible range. Infrared light, or heat, can be detected with instruments that are like night vision goggles mounted on telescopes, as long as the equipment is kept cool. Because of their short wavelengths, X-rays are best detected in space using satellites with reflective optics. Radio waves can also be detected with large single dishes, such as the one at Arecibo, which has appeared in James Bond films, or arrays of many smaller antennae, such as the Very Large Array in New Mexico, which featured in the movie Contact. The Earth itself can also be used as a telescope for detecting fundamental particles that pass through it every day. Physicists have placed traps to try to catch these particles as they pass through. Thank you for watching our video about telescopes. We hope you learned a little bit more about the fascinating world of astronomy and the tools that we use to explore it. Whether you're a beginner or an experienced stargazer, there's always more to discover and marvel at in the night sky. Don't forget to check out our other videos and subscribe to our channel for more interesting content about universe and other scientific topics.